Okay, so now let's look at how we can go about combining chemical equations and how that impacts our equilibrium constant. And there are a bunch of rules you can look up in the book and it'll walk you through it. But I think seeing kind of the logic flow as to where those rules come from will make it easier and probably less confusing when you go to apply them, because it'll make sense as to how they come to be. So we're going to do things, flipping reactions, adding reactions, and scaling reactions, multiplying or dividing by a certain amount. What I want you to do is to hit pause. I want you to write equilibrium expressions for both of these reactions. I want you to find the full and net equilibrium reactions when the two reactions are added. So find them individually and then add them together. And then write a net equilibrium constant expression and a value, or at least kind of think through how you might do that. And then come on back, because I'm going to work that through right now. All right, so first let's start with our equilibrium expressions. So K1 then, let's see, K1 is going to be, let's see, everything is in gas phase. So it's going to be carbon monoxide times hydrogen gas cubed divided by methane and water in gas phase. So notice this gets included. The water in gas phase is not excluded because it is in the same gas phase. And for simplicity, I'm leaving off our phases just so I have enough space to do things here. Let's see, so K2 then is going to be methane times H2S, and that quantity is squared, divided by CS2, 2 times hydrogen gas to the fourth. Beautiful. Now let's add them both together. I'm going to switch pen colors so it stands out a little bit more. And when I add them both together, let's see, I'm going to get CH4 plus H2O. That's the first equation. Then plus my CS2 plus my H2 gas in equilibrium with my CO plus my 3H2 plus my methane plus my H2S. So if I want to write an equilibrium expression for this beautiful combination of chemical elements that are reacting with each other, I'm just going to do the exact same processes I've done before. The only difference is now I just have a bunch more of it, right? So I'm going to have, let's see, my CO, that's my H2, that's cubed, times my methane, that's my H2S, and that is squared, divided by my methane, and my water, gas, I should say, and whoops, CS2, and my hydrogen gas to the fourth. So let's take a look at what we actually have here. If I look at what I have on this side, what I'll notice is this is just my K1. That's exactly what we have written here. And so if I look over here, well, this is just K2 because it matches exactly what we have here. So when I add equations together, my equilibrium constant then is just K1 times K2. So let's just put the values in there, 0.255 times 3.03 times 10 to the negative 5. And what do I get? I get 7.727 times 10 to the negative 6. So let's check our sig figs. I have 3 here, and I have 3 here. So my answer is going to have 3 sig figs. It's going to end at that 2, which would round to a 3 if I was putting it into SmartWorks. Okay. Now let's take a look at one other thing that we can do. I asked for a net reaction on this. So if you remember back to Chem 162, remember when you worked with Hess's law and you would add 2 equations together, you'd be like, okay, I have 3 hydrogens here and 4 hydrogens here. So if I'm adding the 2 equations, that would cancel out with that and would leave me one of those. And I have methane on both sides, so that would cancel out with that. And then my net reaction would be the combination of the 2. So my net reaction then would be H2O plus CS2 plus H2 going in equilibrium to carbon monoxide plus 2 H2S. Sweet. And I can also look at this expression that I've written here. And just because we're doing things in terms of concentrations or anything else that we could do it in terms of, the math rules still apply, right? So if something exists on the top and the bottom, it's going to cancel out and simplify. And if I look here, let's see, what do I have? I have 3 H2s here, so it's going to cancel out with that. 4 minus 3 is 1. And my methanes, same thing. That's going to cancel with that. So what did I do here? Okay, yep, products of reactants. So I have 1, 2, 3. So 3 things here. So this would be my net. And my net equilibrium then is just those removed compounds. So there we have it. So our rule for this then is that if I'm adding 2 equations, then I am multiplying my equilibrium constants together, and I can simplify things that exist on both sides of the equation, just like what we've done before. All right, so now let's take a look at this one. This is going to be my primary equation, and I'm going to do a few things with it to see how that is going to change the equilibrium. The first one out, well, let's just go ahead and write our equilibrium expressions for everything. So I'm going to have Kc1 equals, let's see, the concentration of CO2 times CF4, not CO4. That would be weird. And then divided by COF2 squared. Now what does this one look like? I have Kc2 is, let's see, COF2 squared divided by CO2 times CF4. So let's compare these 2 expressions. If I look at it, what have I done? I've just flipped my equilibrium expression here. From here to here, I've just taken the inverse by flipping it, right? So that means that my Kc1 is, or my Kc2 is just going to be 1 over Kc1. So I have 1 over Kc1. There we go. So if I change the order, I just take the inverse of my equilibrium constant. So that's not so bad. Now what about if I multiply everything by 1/2? So I'm going to have my initial equation, the CF2, I'm going to multiply by 1/2, otherwise known as dividing by 2, right? What do I get here? I get Kc3 is going to equal CO2 to the 1/2 times CF4 to the 1/2 divided by COF2. So what's the pattern here that you see? What have we done to that initial equation? Because what I'm looking at is I look at this and I say, okay, if I took the square root of this side, so this would be 1 over 1 times 1/2 gives me 1/2, okay? 2 times 1/2 just gives me 1. That tells me that Kc3 is going to equal Kc1 to the 1/2. just doing everything to both sides. So the rule here would be if I am doing a factor of a chemical equation that exists, I just raise the equilibrium constant to whatever that factor is. So if it's a half, I raise the Kc to the 1/2. If it's doubled, I would just square it. If it's tripled, so on and so forth. Okay? Let's see, what about the next one? Oh dear, we went all sorts of wild here. We flipped it and cut it in half. Oh my. So Kc4 then is going to be, let's see, the COF2 is going to come up top, divided by CO2 to the 1/2 and CF4 to the 1/2. Okay, so now let's think what we've done to Kc1. Well, we flipped it, so it definitely equals 1 over Kc1. And I divided it by 1/2. So I'm going to raise my Kc1 to that power. There you have it. So if I flip it, if I do more than one thing, I just need to do both steps, if you will, to the equilibrium constant, and that takes care of it. So here are the rules then. Just simplifying, recapping what the rules are then. If you're adding reactions, then you multiply by the K values. If you're doing a reverse reaction, you're inverting the K values. If you're multiplying the reactions by each other, then we're just going to raise the old K to the new number power. And that's it.